So in this lesson, we are going to learn how to divide current between resistors which are connected in parallel. Now, two resistors are said to be in parallel if you have the same voltage or potential difference expressed across them. Now, let's consider a simple circuit where we have two resistors connected in parallel. So we have this to be the voltage source, which is expressed across each of the two resistors. So let's call the first one R1. We have the second one to be R2. Now this voltage source is going to produce current, say I, flowing through the circuit. And this current flows in this direction, that is in the clockwise direction, approaching this node. Now at this node, we have the current dividing, so that we have I1 flowing in this branch, that is R1 through R1, and then we have I2 also flowing in that branch, which is through R2. Now looking at the circuit, you realize that the two resistors R1 and R2 are connected to the same two nodes. That is, they are connected at this node. Let's call this node A, and then again they are connected at this node, that is node B. So you realize that the two resistors are connected to the same two nodes, A and then B. Now when this happens, then we say that the resistors involved are connected in parallel. Now since the two are connected in parallel, it means that we have the same source voltage expressed across each of them, like we said earlier. So if you want to find the current flowing through each branch, then using Ohm's law, which is giving us V equals IR, we can make I the subject, and thus we divide V by R. So here we can have I1 to be equal to V divided by R1, and then we can also have I2 to be equal to V divided by R2. Now, applying Kirchhoff's current law at this node, we have current I entering the node, and then we have current I1 and then I2 both leaving the node. So from KCL, or applying KCL at node A, we can have I equals I1 plus I2. Now let's substitute the expressions for I1 and I2 in here. So that becomes V over R1 plus V over R2. So we can factor out V, and then we have 1 over R1 plus 1 over R2. Now what's in the brackets here is what we call the reciprocal of the equivalent resistance or the total resistance. Now what this primarily means is that we have 1 over Req to be equal to 1 over R1 plus 1 over R2. Let's try to simplify this. So we have the LCM to be R1 times R2. We divide this value by R1, and then we have R2 when you multiply by 1, and then we divide this by R2, and then you still multiply by 1, and then you have R1. So that is equal to 1 over Req, and thus Req is equal to the reciprocal of this. So R1 R2 divided by R1 plus R2. Now what this primarily means is that the combination of two resistors in parallel is given by the product of the two resistors divided by their sum. Now again, if you want to find the total current I here, then what this primarily means is that you have I to be equal to V times 1 over Req, and that is equal to V divided by Req. So basically we are going to substitute this, what we have on the right hand side, in place of Req. So this is the simplified version of the formula used to find the value of I, which is produced by the voltage source V. Now, given 2 or more resistors, then to find the total resistance, that is given by the formula 1 over Req, or better still 1 over RT, to be equal to 1 over R1 plus 1 over R2 plus through 2 plus 1 over Rn. So if the resistors are 2, you can simply use this formula straight away. And if the resistors are more than 2, then you can simply resort to this formula. Now, how do we divide current between 2 resistors which are connected in parallel? That leads us to what we call the current division rule, or better still, the current divider rule. Now, considering this same circuit where we have current I approaching the node, and then we have I1 flowing through R1 and then I2 flowing through R2. Now, 2 resistors are said to be in parallel if, let's say, we have the same voltage expressed across each of them, like we said earlier on. Again, 2 resistors are said to be in parallel if they are both connected at the same 2 nodes. And then lastly, 2 resistors are said to be in parallel if you can go through the loop without passing through any other circuit element except those 2 resistors. It means they are connected in parallel. Now, to divide current between 2 parallel resistors using the current division rule, that is given by, so let's say for I1, that is given by I1 equals, now since you want to find the current flowing through R1, then initially we are going to consider R2, so that is given by R2 divided by the sum of the 2 resistors involved, so R1 plus R2 times the total current approaching the node, which is I. And then if you want to find the current flowing through R2, that is also given by R1 divided by R1 plus R2 times I. Now let's move on as we consider 2 extreme cases when we want to talk about the current division rule, or better still, the current divider rule. So in order to consider those 2 extreme cases, let's redraw the circuit in the first section. So we have voltage V, which is expressed across 2 parallel resistors, R1 and then R2. And we have this to be the total current I approaching the node. We have this to be I1 and then I2. So we are going to consider 2 cases, 2 extreme cases. That is, we have A, when R2 is equal to 0, and then B, when R2 is equal to infinity. So first of all, let's consider A. Now, when R2 is equal to 0, we have the circuit looking like this. So here R1 has a value and then R2 is equal to 0. Now when R2 is equal to 0, we say that the circuit has been short-circuited, and thus the resistance in this branch is virtually close to nothing. It is virtually equal to 0. Now, as the current approaches this node, the current will like to take the least resistant path. So which means that the current will like to flow in the short circuit, ignoring this branch, which is R1. So what this primarily means is that the current I1, which is supposed to flow through R1, is 0 amperes, because all the currents will like to flow through the least resistant path. Therefore, the current I2 will be equal to the full current I. So whenever there is a short circuit, the current will bypass the resistor R1 and then flow through the least resistant path, so that we have the current I2 to be equal to I. Again, when we have R2 to be equal to infinity, then this is how the circuit is going to look like. So we have this to be R1, and this is R2. R2 is equal to infinity. We have current I approaching the node. Now, as the current approaches the node, we have R2 to be infinity, which is a very large resistance value. Now, using the principle of current flowing through the least resistant path, on reaching this node, the current will like to flow through R1 and then ignoring R2 because it is close to an open circuit, so the current cannot flow through an open circuit. So the current will like to flow through R1 and then ignoring R2. Therefore, we have the current I1 to be equal to I, and then we have current I2 equals 0 because no current will flow in this branch. So we call this a short circuit, and that's an open circuit. Now let's move on as we take a few examples. So let's start off with example 1. So we are going to find V1 and V2 and the power dissipated in the 12 ohms and 40 ohms resistors in the circuit below. Now in this circuit, we have 4 resistors in here, 12, 6, 10, and then 40, and then we have one voltage source. Now let's look at how current will be distributed in the circuit. So we are going to have this 15 volts producing current say I, which is going to flow through the entire circuit. Now, upon reaching this node, we have the current going to split. So we have the current flowing through the 12 ohms to be I1, and then let's assume that the current flowing through the 6 ohms will be I3. Now the two current values are going to add up here at this node, and then they further split into I2 and let's say I4, and then they combine here and then move to the negative terminal of the voltage source. So basically this is how current is going to be distributed in the circuit. Now, in order to find the voltage V1 and V2 and the power dissipated in 12 ohms and then 40 ohms, we first of all need to find the total resistance for this circuit, and to find the current I flowing through the circuit, that is the total current I flowing through the entire circuit. So let's do that together. Now let's call the combination of these two resistors RT prime and the combination of these two resistors RT prime prime. Now you realize that these two are connected in parallel because first we have them connected at the same two nodes. Secondly, you can go through the loop without passing through any other circuit element except two resistors, so they are connected in parallel. So let's say RT prime is equal to 12 parallel 6, and that is equal to 12 times 6 divided by 12 plus 6. Now 12 times 6 is 72, 12 plus 6 is 18, 72 divided by 18 is 4. So this is 4 ohms, and then we have RT prime. The two are also connected in parallel, so you have 10 parallel 40, that is equal to 10 times 40 divided by 10 plus 40. 10 times 40 is 400, 10 plus 40 is 50, 0 cancels out 0, 5 goes here once, 5 goes here 8 times, so this is 8 ohms. Now let's try to redraw the circuit. So we are going to have something like this. We have the 15 volts, and then we have the combination of these two resistors here, that is 4 ohms, which is now in series with the combination of these two, so that is 8 ohms. So you realize that the two resistors are connected in series because you have the same value of current I flowing through them. So we have I, which is the total current, to be 15 divided by 8 plus 4, so that's 15 divided by 12, and that's equal to 1.25 amperes. So we have RT, which is the total resistance, to be RT prime plus RT prime prime, and that is equal to 4 plus 8 equals 12 ohms. So this is that 12 ohms. So we have the total current I to be 1.25 amperes. So that is the total current I approaching this node, 1.25 amperes. So as it gets to the node, it splits. So we have I1 flowing here and then I3 also flowing here. Now we want to find the current flowing through the 12 ohms resistor, because that is where our interest lies. So it means that we are going to apply what we call the current division rule. So for current I1, that is equal to, using the current division rule, we are going to have the value of this resistor, 6, divided by the sum of the two resistors times the current approaching the junction or the node, which is I, that is 1.25 amperes. And so when you do your calculation, you realize that you have I1 to be 0.4167 amperes. So that is the current flowing through the 12 ohms resistor. Now we are asked to find the value of V1 and then the power dissipated in the 12 ohms resistor. So for V1, we have V1 to be equal to the value of current I1, which is 0.4167 times 12, and that is equal to 5.0004 volts, which is nearly 5 volts. So we say that V1, or the voltage across the 12 ohms, is 5 volts. Next, we want to find the value of the power dissipated in the 12 ohms resistor. So that is given by power in 12 ohms is equal to, power is given by I square R. So I square times R. So we have I to be 0.4167. So the square of it times R, and then R is 12. So that also gives 2.084 watts. So that is the power dissipated in the 12 ohms resistor. Again, let's move on to V2 and then power in 40 ohms. So for V2, now before we get to V2, the current I1 and I3 are going to combine here. So after combining here, we still have I to be 1.25 amperes, and they are going to split into I4 and then I2. We are interested in I2. So using the current division rule, we have I2 to be equal to this resistor, which is 10, divided by the sum of the two resistors times the value of the total current approaching the node, which is 1.25. So 1.25 amperes. So this is times 1.25 amperes, and then we have I2 to be equal to 0.25 amperes. 0.25 amperes. Now the voltage V2 is equal to 0.25 by 40, and that is equal to 10 volts, and then power in 40 ohms is equal to 0.25 square times the resistor 40. When you multiply the two, you have 2.5 watts. Now let's move on to the next question, or the next example. So let's try example 2 together. We are going to find the current I in the 50 ohms resistor in the circuit below. So as usual, we need to find the total resistance for the circuits, and then we try to find the total current, and then based on that we can find the current I, which is flowing through the 50 ohms resistor. Now let's try to distribute current in the circuits. So we assume that this voltage source produces current, let's say IT, which is total current, and then on reaching this node the current splits. So let's say we have here to be I1, current flowing through this branch to be I1, current in this branch to be I2. The two current values combine here, and then we still have IT approaching this node. At this node we have I1 flowing in this branch. So let's say current flowing through this branch will be, we have I1, I2, so I3, and the next one will be I4. So that is how current will be distributed in the circuit. So 1, 2, 3 current combine here, and then they move to the negative terminal of the voltage source. So let's try to find the total resistance for this circuit. So we have these two resistors connected in series because we have the same current flowing through them. So we are going to have this to be 60 ohms. Now these two are in parallel. These two resistors are connected in parallel. Now whenever you have two resistors connected in parallel which are of the same value, then the parallel combination is basically half of the two values. So we can have 60 parallel 60, which is equal to 30. Now remember that when you are solving any question or when you are doing an exam, try to do the correct calculation, that is 60 by 60 divided by 60 plus 60 to arrive at this value. And so also at this point we have these three resistors connected in parallel. So first of all, let's try to have the parallel combination of these 200 ohms resistors. So that's going to be 100 by 100, that is 100 parallel 100, and that is equal to 50 because they have the same value. So that is 50 ohms. So this is the parallel combination, which is 50 ohms, and then we have that in parallel with another 50 ohms. So that becomes 50 parallel 50, and that is equal to 25 ohms. Therefore, if you want to redraw the circuit, then we have this 110 volts, 110 volts, and then we have the first resistor combination to be 30 ohms in series with the second resistor combination, that is also 25, so 25 ohms. Because the two are in series, we have the total resistance to be 30 plus 25, and that is equal to 55 ohms. Therefore, the total current in the circuit IT is equal to 110 divided by 55, and that is equal to 2 amperes. So that is the current produced by the 110 volts, 2 amperes. So we have 2 amperes approaching this node. The 2 amperes splits, and then the two current values combine here so that we still have 2 amperes flowing or approaching this node. Now at this node, remember that we first combined these two resistors. So we can redraw this as, let's say, having the diagram like this. Where this first 50 is this branch where we have current I flowing through, and then the second has to do with the combination of 100 and then 100, so that is 50 ohms. And then we have current IT approaching this node. So if you want to find the value of current I, then using the current division rule, that is basically the value of the other resistor, which is 50, divided by the sum of the two resistors, 50 plus 50, times the current approaching the node, which is 2. So this becomes 50 over 100 times 2. 50 times 2 is 100, divided by 100 is 1. So therefore we say that the current I flowing through the 50 ohms resistor is 1 ampere. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.